In this section, we'll take a look at the Spanning Tree Protocol Concepts objective of the JNCIS Service Provider exam. We'll examine STP, RSTP, Mstp, and Vstp, and we'll also take a look at spanning tree security. For more detailed coverage of this objective and more, please check out the Juniper Service Provider Switching course. In this video, we're going to take a look at spanning tree. And spanning tree is a protocol that allows us to calculate loop-free topologies over physical topologies where we have resilient interconnectivity running between multiple switches. And spanning tree is covered by the IEEE standard 802.1d. Spanning tree is facilitated through the exchange of BPDUs, or Bridge Protocol Data Units. And these aren't flooded in a switch environment. What happens is that they are exchanged between neighbor devices, and then those BPDUs are passed by those neighbor devices. Some parameters in them are modified, and then they are sent out of other ports. So in our network here, for example, say this device here is sending a BPDU. He sends it out of this port to this neighbor. This device passes that BPDU, and he then in turn sends out his own BPDU out of this port. And this way, the BPDUs gets to arrive at all of the different devices in a spanning tree speaking network. So let's now talk about the steps by which spanning tree can find a loop-free topology within a physical network. So if we look at the example network I've drawn on the board here, we have a ring of switches interconnected. And if we didn't run spanning tree, we would quickly see layer 2 loops in this environment, and the switches would become overwhelmed with looped traffic. This device would send a packet out, this switch would forward it, this switch would forward it, and so on. So this is why we need spanning tree. So the first step for spanning tree to operate is that we need to elect a root bridge. This is this step here. So essentially, the root bridge election is controlled by a root priority value, and we're preferring the lowest priority value here. And if there is a tie break with the root election, we're going to tie break on MAC address. So in our example network here, switch 1 has the lowest root priority, so he is elected as the root bridge. What then happens is all ports on the root bridge go into designated port mode, and designated port mode means that these ports are forwarding. So all ports connected to the root bridge are forwarding. The next step in the spanning tree operation is that all other switches in the network need to nominate a root port, and the root port is their port that's closest to the root bridge. This is determined because every port on every switch has a cost associated with it. This can be dynamically determined by bandwidth, or it can be manually configured. And we determine the cost from every switch in the network to the root by adding the cost of the ports that have been traversed by the BPDUs from those switches to the root. And this additive increase of cost of all the ports that are traversed by BPDUs gives us the total root cost. And the port with the lowest root cost on every switch becomes the root port. And root ports are also placed into forwarding state. And then the final step of the spanning tree process is that we then look at every LAN on the network. And for every LAN on the network, we first elect a designated bridge. And a designated bridge is the switch, is the bridge that has the lowest root cost to the root bridge. So in our example here, we're looking at the LAN in between switch 2 and switch 3. Switch 2 here has the lowest root cost up to the root compared to switch 3. Therefore, switch 2 becomes the designated bridge, and his port on the LAN becomes a designated port, so he is then placed into forwarding state. All other ports in the network are then blocked, as is the example here on this switch 3 facing into this LAN. He goes into blocking mode, and this then removes the loop within our architecture here, and so it means that we can forward layer 2 frames through this network without any loops existing. And this is a quick overview of the operation of the spanning tree protocol. In this video, we're going to talk about rapid spanning tree, or RSTP. As the name would suggest, rapid spanning tree provides some convergence improvements over standard spanning tree. And these improvements were needed because standard spanning tree takes around 30 seconds to converge, and 30 seconds downtime in a modern network is definitely not acceptable. And rapid spanning tree improved on these convergence times through a number of different means, and we'll talk through these different techniques in this video. So firstly, in standard spanning tree, you have these 5 different states that a port iterates between as it's moving from coming online initially to being allowed to forward traffic. We have disabled, blocking, listening, learning, and then forwarding. And the first thing that happened with rapid spanning tree is that we merged these 3 states into one discarding state. The next enhancement was that we could nominate certain ports as edge ports. So these will be ports that are interconnected to non-switching devices, so connecting immediately to PCs, to servers, for example. And edge ports will immediately transition to forwarding as they come up. They don't have to transition through this state machine before being allowed to send and receive traffic. So this allows edge devices to come up and become operational as soon as they are plugged into the network. And the next improvement was adding some additional port roles to the ones that we've already seen with standard spanning tree. So these are these roles here. So let's examine that on the right hand side of the board now. We still have our root bridge, our root switch. We still have our root ports, which are the ports with the lowest port cost on a given switch to the root. And we still have our designated ports. So those are the ports on the designated bridge, the bridge with the lowest root cost of all the bridges on a given broadcast network. And the designated port is that port that's connected to that designated bridge on that LAN. But we're now introducing 2 additional port types. We have the backup port, and a backup port is providing backup to designated ports. And backup ports are in blocking state as long as they're receiving superior BPDUs from the same switch. And then we have alternate ports, and alternate ports are backing up root ports. And alternate ports are always in blocking state as long as they are receiving superior BPDUs from other switches. So with all these improvements in place, rapid spanning tree can converge significantly faster than standard spanning tree. One final thing to note here is that we can't interoperate rapid spanning tree with standard STP. So if we have a mix of switches, some that support rapid spanning tree and some that don't, what happens is that the switches speaking rapid spanning tree, on receipt of legacy BPDUs, revert back to standard spanning tree. That way we're not going to get any issues with the interplay of rapid spanning tree speaking devices and standard spanning tree speaking devices. And this was a quick overview of rapid spanning tree. One problem with either spanning tree or rapid spanning tree is that we have a large amount of deployed capacity that we're not using. With our interswitch links, there are a lot of ports that are in a blocking state at any particular time within the network. So we need an approach to better use our installed capacity to maximize the amount of investment that we've placed in our network. And we can do this with one of two protocols, both of which we'll spend a bit of time talking about in this video. And both of these protocols solve this problem in a similar manner. What these protocols do is that they have different topologies. A topology could be a group of VLANs or a single VLAN, and they have different topologies having different port states. So for one topology, one port could be blocking. For a different topology, that other port could be forwarding. This way, we have some traffic associated with a VLAN or a group of VLANs forwarding traffic on one set of ports, and we have another group of traffic associated with a group of VLANs or another VLAN forwarding on another group of ports. So this way, we're having all our ports in our network that are physically deployed carrying some traffic for a particular VLAN or a particular group of VLANs. And this way, we are maximizing the amount of physical installed capacity that we have within a network. So this is the theory of both of these protocols. Let's dive into them in a little bit more detail. So the first is multiple spanning tree, or MSTP. Now this is a standards-based protocol, so you can use it in a multi-vendor environment. And what we do here is that we are mapping groups of VLANs to instances, and we have a different topology for every instance. Within a multiple spanning tree domain, we have the concept of regions, and an individual region is a group of switches that have the same region name, that have the same revision number, and have the same VLAN to instance mapping. And we can have a maximum of 64 instances per region within a multiple spanning tree domain. One of the big benefits of multiple spanning tree is that you can have it interoperate with standard spanning tree through a process of deploying something called common spanning tree. And what you're doing here is that you effectively treat the multiple spanning tree regions that you've deployed as virtual switches. And these virtual switches then interconnect via common spanning tree to your switches that are not capable of running multiple spanning tree and that are running standard spanning tree. And that way you can still have a complete loop-free layer 2 network, but you can have a mix of devices that are running multiple spanning tree and devices that are running legacy spanning tree. So that was multiple spanning tree. The second protocol that we can use is VLAN spanning tree, or Vstp. Now Vstp is Juniper proprietary. However, it is possible that you could use it in a multi-vendor network in conjunction with other vendor proprietary protocols, such as PVST. And what we're doing with Vstp is that instead of having groups of VLANs mapped to different topologies, we are having a different topology per VLAN. So the one main thing to note with this is because we are having different topologies per VLAN, if we have many VLANs deployed, this can have an impact on the CPU of the control plane of our switches speaking Vstp, because we're having to calculate different topologies for perhaps many thousands of VLANs. This is a quick overview of how you can deploy either Vstp or MSTP to maximize the deployed physical assets in a layer 2 network. When devices are connected to a spanning tree network that are misconfigured, or certain partial failures occur in a spanning tree network, These issues can sometimes result in catastrophic failure of the entire layer 2 domain, and this is obviously highly undesirable. We need to turn to things like spanning tree security to try and make our layer 2 network, speaking spanning tree, less brittle and more resilient to any kind of misconfiguration issues that might happen in the network itself or on interconnected devices. And there are three main types of spanning tree protection that you can deploy on Juniper devices. The first is root protection. Now, on your spanning tree network, you are going to typically have certain devices that you want to be the root bridge and certain devices that should never be root bridges. Typically, you want your core switches to be potential root bridges, and you never want your access layer devices to be root bridges. So in this case, if you deploy root protection on the ports facing switch devices that should never become the root bridges, what happens here is if we ever receive a superior Bpdu on those ports with root protection enabled, then those ports are put into blocking state. This means that if an access switch is incorrectly configured with a spanning tree priority that's going to beat one of the designated root bridges, then the resulting superior Bpdu from that misconfiguration, rather than resulting in a massive topological change in the network, just results in that access switch being isolated from the network, and that fault can then quickly be rectified. The next type of protection is loop protection. So this is there for cases where we have partial failures of links that result in a link being able to still forward traffic, but a link not being able to process, i.e. send or receive Bpdus. And the loss of Bpdus means that ports that aren't meant to can transition to designated port state, and that can mean that we can easily introduce layer 2 loops into our topology. So loop protection comes to our aid in this case, and what we do with loop protection is we turn this on ports that should never be designated ports. So these are ports that are alternate ports for root ports, for example. And what loop protection means is if we ever stop receiving Bpdus on a loop protection enabled port, what happens is that we then shut that port down. We put that port into blocking state, and this prevents any routing loops from resulting. And then finally, our third spanning tree security mechanism is Bpdu protection. And we would enable this on any edge port that's connected to a device that should never be sending Bpdus. So these are your ports facing your PCs, your servers, etc. And this stops any misconfiguration. This could be resulting from a physical loop being introduced incorrectly. It could also mean that the PC or the server has been incorrectly configured. Maybe it's running a hypervisor layer like KVM, and it's got some virtual switching configuration going on there, and it's sending Bpdus. These could quite easily cause massive topological issues in our network. So instead, what we do is that we know that we should never receive Bpdus on these ports. So with Bpdu protection enabled, as soon as we receive Bpdus on these ports are again put into blocking state. And this means that we're limiting the spread of any service degradation. We're isolating only the misconfigured element. This is a quick overview of some of the different types of security that we can deploy with spanning tree.